So that's one thing. I've also emailed Dr. Day an Excel spreadsheet where you can actually use Bernoulli Euler beam and get natural frequency and mode shapes of, say, composite towers for wind turbine. I think you might then email it that because that's a soft. You can't give you a hard copy of that, so obviously it has to be emailed or somehow transferred electronically to you. So that's the second thing. The third thing is there is an assignment I gave. You don't have to solve it right now, but this is based on the aeroelastic code, which was developed by National Renewable Energy Lab in Colorado, USA. And I'll show the website of that, and you can register and download their software. You can run it for various conditions to get the wind turbine response. And then the fourth thing is I'll also show you the OpenMove website, which is our software for analyzing mooring cables, and you can couple your model with the mooring cable model and analyze wind turbines and other offshore systems. So, so the first two things done, one handout given to you. The second Excel spreadsheet will be also given to you in some way. Let me show you the, connect this to the, sorry, I think this is not working yet, so I'll show it to you at some point in time, either today or tomorrow. The openmove.org, but you can try it looking at it, www.openmove.org. Another one is enrel.com. See exactly what the website is. So this is the one. So this is openmove.org, and there's some problem with the presentation, but don't worry because we're not going to look at the screen too much, obviously. And obviously, you can recognize me here, same photo. So this is an open source code that will be linked with the DLLs in MATLAB, Python, and C++. And then you can so you can download it from GitHub as well. Okay. And there are available as well. I think we haven't uploaded those yet, but these are some of the publications. So these are what some of the results I showed are based on. So you can go through these papers as well. This is in wind energy, channel of sound and vibration, international channel of fatigue and ocean engineering. There's some conference papers, including one on the development of the software itself here. And again, these are not available yet, but I think if you go to the code and look at so the source code is available from here. Okay. So this is OpenMove, obviously. And then the NREL one is this NWGC NREL.com. And actually, the fast code is available from NREL. NREL also has a finite element code for tower and plate. It's called the B mode, which is very similar to in structure what I have in the Excel. And they also have wind data and other things as well, because obviously they have more resources. So this is where you can get the fast from. So you can register and then logging in, you can download the software. So this is a US government funded for land-based turbines and offshore turbines. So this is Aeroteam, where it simulates the wind data, and it is connected to Adams, which is a finite element software. Then various versions of Aeroteam. BeamGene is a finite element software. B-Modes is one, as I said. The FAST is the aerodynamic code, which is pretty much what I did here actually. So FAST exactly does what I showed in my structural modeling, both for onshore and offshore, with this distributed degrees of freedom. So they have, I think, about say 13 degrees of freedom model, because they're more modes, that's it. And then we also have drivetrains and other things which they have. So yeah, so really these two are the things I wanted to show you, and I've given you some more information. And then discussion about tutorials and so on. There's been one question about one tutorial somebody has asked, so I'm going to solve that. I think it's tutorial. Is it tutorial number 3? Yeah. So the first tutorial was on the wind data, which all of you have done. The second set of tutorial with a lot of small problems like Reynolds number, calculating the wind profile, or spectral density function. This third tutorial given on mainly on aerodynamics and BEM and so on. So the third problem of the third tutorial sheet. And the fourth one is related to fast code. So if you download the fast code, you can do it, or you can independently code things based on the formulas or based on the formulation that you derived this morning. So currently, based on the question of the query, I'm solving the problem 3 of problem sheet 3, right? Problem sheet 3 and problem 3. Is that correct? And I think the problem. So maybe I'll just read the problem first and then we can solve it. So the problem says that a symmetric equal to 4 degrees. I think the degrees didn't come out well here, but it's 4 degrees. So find the moment per unit span, go to point X that is located at 0.75 C back from the leading edge. That is the fractional distance of X from leading edge is 0.75. So it's actually located at a point which is 0.75 of the total port length. So if I draw the airfoil, so it's an airfoil. So this is assignment number 3, and this is problem number 3. So if I draw the airfoil, it's a symmetric airfoil. And the chord length C is given as 2 meters. Okay, and what we have to find is the moment at point, which is 0.75 C from the leading. So this is my leading edge. And the point is somewhere here. So this is the point X, located at 0.75 C. And the problem is that we have to find out what Nx is at this point. We're also given that the angle of attack is 4 degrees. And the V relative is 40 meters per second. Okay. So obviously, we use the moment equation for airfoil. If you look at I think lecture day 2, lecture 2 actually. And so we'll be using the moment transfer equation, saying that moment at A is given by moment at B plus, this is L times HA minus HB times C. But C is the chord length, HA and HB are the relative percentage corresponding to the chord, location of A and B, and L is the lift. So L is the lift, and these HA and HB are the 2 percentage locations from the leading edge in terms of the percentage length of the chord. Okay. So now, by definition, we know that the center of pressure is the point where the moment is 0. Right? So there are 2 things. One is the aerodynamic center, and aerodynamic center is the point where if we take the rate of change of the aerodynamic moment coefficient at that point with respect to the angle of attack, then we get that as 0. So T alpha of the moment at the aerodynamic center is equal to 0. And we also know that center of pressure is the point where basically if you apply a load, only translation will be produced, no moment will be created. So by definition, can you see if I write at the bottom of the, so by definition, we know that the moment at the center of pressure is 0. Okay. Also, we have a symmetric airfoil. And if you have a symmetric airfoil, then we also know that the percentage distance from the leading edge where we have the center of pressure is given by 1/4. So it's somewhere here. This is C over 4. So we're going to use these information, and then applying this, feeding it back to the main equation. Obviously, we know that we want to transfer the moment at the center of pressure to this point X here. So obviously, Mx is equal to, the moment here is 0. So obviously, we have a 0 term here, plus we have the L lift, and we know that this point is at a distance of 3/4 because 0.75 C is 3/4. So this is 3/4, and this is C over 4, which is 1/4 times C, which is basically something like, if I take this difference, it's going to be 2 over 4, which is half. So I have L multiplied by C over 2. The C is the chord length, and L is the lift. So chord length is known. So what we need to do now is find out what the lift is going to be. And we know that the expression for lift is given by, should I go to the top actually? It's easier for you to read that. So the expression for lift is given by L is equal to, obviously we take the stagnation pressure first, which is half rho, and in this case the relative velocity squared. So half rho V relative squared, and then you have to use the coefficient of lift CL, and then multiply it by chord. So question then is, how do we find CL? I think that's where we got stuck probably. That's really the question was. So since the airfoil is symmetric, so we can say that airfoil is symmetric, and also we know that angle of attack alpha is small. It's less than 6 degrees. So alpha less than 6 degrees. So in this region, if you recall, the lift coefficient looks something like this. So CL versus alpha is actually almost linear, and then it goes like this and something like this. So you're in this region. So what is the slope of this line? It is 2 pi, right? Well, yeah, I mean, the slope is 2 pi. So CL is 2 pi alpha. So this slope is 2 pi. So CL can be then assumed as 2 pi alpha. So really now we have everything, because we know rho, we know velocity, we know the CL, because we know alpha, we know C. So if you substitute this in this expression here, then we should be able to calculate M. So if I just substitute everything here, L comes from there, so half times rho is 1.225 times, does anybody have a calculator? 40 square multiplied by 2 pi. Alpha is 4 degree, but we have to change it to radian. So we know that so 180 degree corresponds to pi. So pi divided by 180 multiplied by 4. And then we have to multiply this by C. And C is 2 meter. And then we have finally C over 2 coming from here. So it's going to be 2 over 2. Okay, so this 2 can cancel with this 2. The 2 here will cancel with another 2. But you can do a rough calculation. So I think it's 40 square is 1600, roughly speaking. And 20% of that would be 1920. Pi square is 10. So 4 over 18 is to cancel with this. Is roughly 1/4. So much is it? 429, whatever it is. So it is approximately then 429. Now this is a moment, so obviously it's kilo. So Newton meter, because everything is in meter, Newton here. So Newton meter, and because per unit span, so per meter. We're taking 1 unit span here. So we're taking cross section is there, one, so 1 meter here. Okay, so I think that's what it is. Okay, so I have given you all the information I need. I wanted to give you in terms of the gearbox data, the Excel spreadsheet. I mentioned to you about 2 websites. One is ours, which is openmoon.org. If you're working in offshore and want to couple it, you can get the code. And if you have any problems, you can also contact us. If you're using our code, then you should refer to that as well, okay? Either to our papers or to the website. And also, I've given you the Enroll code link, so you can also register and download. And the 4th assignment you can do once you have the fast code. But you can try that out. You don't have to solve it right now. The main assignments are basically assignment 1, 2, and 3, which basically will forward with the lectures. Okay. So I think that's it from my side. So do you have anything else to ask now? Because I think we have another maybe 20, 25 minutes before we start the exam. Unless you want a short break before the exam. I think assignment 2 was pretty simple. They're very small problems based on simple calculations, and if you go to the lecture notes, fine. Assignment 4 is the fast we have discussed. Assignment 1 we have discussed yesterday. So the only thing left out was assignment number 3. And we have discussed one of the problems, and I think others are pretty similar. You'll be able to do those. This one on aerodynamic moment, aerodynamic center. For that, you have to make sure that dt alpha of m aerodynamic center is equal to 0. That will give you the solution. And there's one problem on BEM with the correction. But I think that is also relatively straightforward. Just the thing is that you have to do an iteration. Did any of you try that one? The last problem for assignment 3. Well, what you could do is you can do that tonight, and we'll have chance to again meet tomorrow. You know? I want to ask you, but I think it should be okay. So, okay. So, do you have any other questions now, or do you want to discuss any other problem state? Well, if not, then maybe I'll just hand it over back to Dr. Day again. And I think we are mostly done. So maybe, I don't know if you want to give a 15-minute break to then before the exam starts then. So do you want to give them a break of 15 minutes? We can start at 1.
If you want to have some break for around 10 to 15 minutes, you can have it. That's what your preparation. Just make up your mood and mind before starting. Although it's open, so you need not to worry about it. You have your study materials. But seeing that, you need to inculcate those problems and get the solution. And there are two important announcements. One is regarding some tutorials and assignments. I have sent all those soft copies to your email as well. Just check your email, you'll get that. If not, just tell me by today or by tomorrow morning. I'll send it. Okay, I have already sent it. So those who have not got, only for you. And if you want the soft copy, you need the soft copy of the slides also. that will also be provided to you. So that will be sent through your email, or if you want, or you can get it through your pen drive also. So pen drive will be given to you tomorrow. Okay.